Welcome back. So we are looking at Taylor and Maclaurin series. So the first part of this is looking at functions as power series, and that is something that we actually alluded to earlier, which is really fun, because we were thinking about like our polynomial approximation for like e to the x. So remember that, where we were matching up a polynomial, which was effectively a line, with our e to the x function. And so if you match it up somewhere, then it's possible to get, an approximation for what that function can be. And the way that we matched it was using our first derivative. But what if you also matched the second derivative at that location? And what if you also matched the third derivative at that location? So you can build a polynomial that matches a not polynomial function. And so that's what the first section is about. It's very exciting. And then we're going to look at Taylor series, Maclaurin series, and then remainder. And then we'll call it a day. This one might be kind of long. Sorry in advance, but that's what it is. So the first part of this is if you want to click on this link, and I'll probably link it somewhere else as well. But pause on line notes is very helpful for this section. I think the way that they write it out is very nice. All right, let's get started. So if we want to represent a function as power series, and we know that we have geometric series that converge, and we can figure out exactly what they converge to, that's really nice. And so if we have, I don't know, like something else, right? So if we were taking this general format of what's on this right side, and we're just going to throw it into something else, we can do that by saying that a is 1, so this a, this numerator here, and what we're multiplying by out here is 1, and r is going to be x, and x is our variable, so that changes. So that means that we have a particular interval where our series will converge. Otherwise it won't, because whenever we have absolute value of r is 1 or more than 1, then we end up with a divergent geometric series. So we can take this function and we can represent it as this power series. And that is super duper cool. Like, we have this rational function now, we can represent it as a polynomial. And that's so much easier to work with, because we can take derivatives and we can take integrals of polynomials so much easier than doing stuff with this, which would involve like a u substitution and like more things for integrating, and it's a lot. So having a power series in order to represent a function is pretty great. So for this example, we want to find a power series representation for this function that is not the function that we were looking at before, right? We were looking at the function 1 over 1 minus x. So this is a different function, bummer, but that's okay. I think we can handle it. And we also need to determine its interval of convergence. So what we could do is we could say, okay, this is 1 over 1 plus x cubed, which is the same as 1 minus negative x cubed, right? Subtracting a negative is the same as addition. And now we have this difference, right? So we can have, like, if we think about this x as this negative x cubed, then with our power series that we were looking at before, right, this one, that represents this function, which in our minds can be this parent function, then we can rewrite g of x in terms of that, where we replace our x here with negative x cubed, and raising that to the n power, and we're going from n equals 0 to infinity. And this, I guess we can massage it a little bit more, so we can figure out, a little clearer what's going on. So that is equal to our sum from 0 to infinity of negative 1 to the n power times x to the 3n. And so that's good, right? So now we have an alternating series. So that gives us, I guess, something else to work with. And then we also know, well, we know that this is going to be going to help determine what our interval of convergence is going to be, because this still needs to be x cubed is our r, so we have this x cubed that needs to be absolute value of x cubed that needs to be less than 1. And when is that going to happen? Well, when x is less than 1. The absolute value of x is less than 1. And so, well, there we go. We have our interval of convergence for our power series representation of g of x. And sorry, the numbering is off, but this is the next example. So we're trying to find a power series representation for this function and determine its radius of convergence. Remember, the radius of convergence is how far from the center we have to the end of our interval of convergence. So let's see. Well, let's think about this. What is this? This g, that looks like this our derivative, right? That looks like it's a derivative of maybe the 1 over 1 minus x, right? It's another way that we can think about that. Because if you take the derivative here, what do you end up with? Well, you have the power rule and you have chain rules so that you cancel out the negative, and then you just end up with that. And so, if we know that we have our power series representation of 1 over 1 minus x is going to be from 0, the sum from 0 to infinity of x to the n power, right? That's what we established before. So if we take the derivative of this function here on the left, then we're also taking the derivative of our series on the right. And we know we can do that, right? We saw before that that's something that we're allowed to do. So this, if we're taking our derivative, d dx, this side, and then d dx on this side, then we end up with g of x on the left. And then on the right, we should have something equivalent, which is our sum from 0 to infinity of n times x to the n minus 1, because it's the power rule, right? Oh, wait, no. What happens? Because if we plug in 0, then it doesn't really change anything, right? Because we have 0 times whatever. So our first term is actually doesn't have any value. So we can start our index at n equals 1. And that actually, I mean, it doesn't really matter in the sense that those two sums are the same, starting our index at 0 versus starting our index at 1. But yeah, that works, right? Because now we have, well, we have a geometric series. And so we can figure out what this converges to as well. But we were actually just looking for a radius of convergence, and our radius of convergence is not going to change, because we know that our radius of convergence for a function, its power series, its derivative, and that's that power series, and its integral in that power series, those radiuses of convergence are all the same. The interval of convergence is going to be the same except for maybe at the endpoints. So if we're just looking for the radius of convergence, the radius of convergence is 1, because it's the same as what we had before for our power series for that, which we had our interval of convergence was from negative 1 to 1, and so our radius of convergence was 1, and we were centered at 0, right? Because our center here of whatever we're raising to the n power, that's going to be 0 when x equals 0. Okay. So I promised that derivatives would happen, and so here they are. So we have Taylor series and power series, Taylor series and Maclaurin series. Taylor series are like the more general case, and the Maclaurin series are a particular case of the Taylor series. But something special about it is that with Maclaurin series, we're centering at 0, whereas with Taylor series, we're centering at x equals a. So let's, oh, and the pictures of Taylor and Maclaurin are up because the wig is going to help you remember which one is centered at 0. The Maclaurin series, because Maclaurin's wig makes his head look like a 0, is centered at 0, and then Taylor's head is not shaped like a 0. So that's the silly way to remember that. Okay, so we have Taylor series for our function f at a is given by this. And let's break down this notation a little bit. So we're still looking at our index of summation starting at 0 and going to infinity. So we're adding up an infinite number of terms. And that's the thing that we do in calculus, though, right? We add up an infinite number of things. For integrals, we take an infinitely small look at a slope. That's a derivative. And now we're just adding up an infinite number of terms. That's fine. Okay, so we're going from 0 to infinity. What are we looking at for our terms? We have f, and then we have the nth derivative of our function f, evaluated at a. So we're evaluating where we're centered at. Divided by n factorial. And where is that n factorial coming from? Well, you can think about it now a little bit, but it's going to come out from the power rule. Because when we're taking our derivatives, we're actually going to be multiplying repeatedly by increasing powers. So we're going to end up with a factorial that we need to divide out. And you'll see that actually when you're constructing your power or your Taylor series representations for other functions. So you'll get there. So we have that. So our nth derivative evaluated at a over n factorial times x minus a. So we have an x term, and then we're taking a difference with that and what we're centering at, raising that to the nth power. So you start at 0, right? Because what do we do when we see a series? We write out some terms, because that's responsible. And so our 0th derivative is just our original function. So we have our function evaluated at a, divided by 0 factorial. Remember, 0 factorial is equal to 1. That's a good question. I don't know why, but you can journal about that. That'd be lovely. And then you look at that times x minus a to the n power, but in this case, n is 0. Raising anything to the 0 power is 1. So we just end up with f evaluated at a. That's our first point. And that makes sense, because then we're anchoring the value of our function that's a polynomial to match exactly what the value of our function that is not a polynomial is. So, like e to the x, well, we are anchoring that at x equals 0. That means that we need our function that we're constructing as an approximation for e to the x to match the value of e to the x at x equals 0, which is 1. So a really terrible approximation for e to the x is just the line, 1. And then you also have the first derivative times x minus a to the first power, and you're dividing by 1 factorial, which is again 1. And you're adding that to the second derivative evaluated at a, divided by 2 factorial, because that's the number of the derivative you're taking, times x minus a to the second power, and so on, until you get to the nth derivative, and so on, because our n is actually going up to infinity. If all of these x minus a's became x minus zeros, then all of our terms in here, all of our terms in there, and there, and there, and there, those would just be x's. And all of our a's, all of these we will be evaluating at x equals 0. So I think Maclaurin series just look a little cleaner, so that's my personal preference. I think they're better. But the general case is also very important and super duper helpful. You will come back to Taylor series if you're taking any math classes beyond your regular calculus track. And I highly encourage all of you to do so, because I think you're capable of it. So Taylor series will become a more familiar friend. Right now, it's a lot, because it's derivatives and it's power series. But hopefully it makes sense that we're just taking a function that is not a polynomial, and we're making a polynomial with an infinite number of terms that approximates pretty dang well, actually, like, exactly can be equal to, because we're looking at an infinite number of terms, that non-polynomial function that we're thinking about. And this is how I think computers handle all of our transcendental functions. So that's good, right? Understanding that a computer has a pretty dang good approximation, but we won't be getting your exact function values, just knowing that limitation, but at the same time, very handy tools. But remember that Maclaurin series are centered at 0 because the wig game for Maclaurin is very circular. And then this is Taylor. So, we also have our nth polynomials, where we're looking at capital P sub n, so that's our nth of whatever, so this is a finite polynomial. And these polynomials we're constructing in the same kind of manner of thinking about where we're centering at, and that's the difference between our Taylor and our Maclaurin. We have a capital P with a subscript n, because that's how many terms we're ending up with. And all our terms have this same format of f, the nth derivative of f, evaluated at some number, be it a or c or whatever, over n factorial, because that's how many derivatives you're taking, times x minus a to the nth power, and we're looking at a sum from 0 to infinity of that. But instead of looking at the infinite number of these, we're just looking at a finite n is less than infinity number. And with our Maclaurin series, with our Maclaurin polynomial, it's a polynomial with exactly the same things, except we're also centering at 1. What you use for how you represent this centering, I don't really have a preference. I think the C is a little bit more intuitive because you're looking at something where C stands for center. But it is also important to not really be fixated on like a particular value or a particular representation, because every book that you're going to read is going to have a different way of representing the exact same thing. So have some mental flexibility, because it'll really, really help. Like, understand how to detect the patterns. Keep in mind the general format, but don't get hung up on little details like, do I use C? Should I use A? Just keep track of it. So, we also have this theorem about uniqueness, where if we have our function f that has a power series and is converging on our open interval, so it's not just our trivial case where it's converging for that one spot, right? Because we have 3 different versions of what can happen with a power series. It can have like kind of trivial convergence where it's only going to converge at that one location. We can have an interval of convergence, or we can have convergence for all of our numbers that we're thinking about. And so if we have our function that is represented by a power series and it converges on our open interval, so we have an interval of convergence, then that power series that we have is a Taylor series. And so the Taylor series for f at that location A. And remember that our Taylor series means that we have our function with its derivatives such that it matches up with what our function value is. Okay, so let's look at an example where we have our function 1 over x squared, and we're looking at centering at x equals 1. So try to come up with the Taylor polynomials for of 0 degree, 1, 2, and 3. So you should end up with 4 different polynomials, and let's try it out. So pause the video and try that. So our first Taylor polynomial is really easy, our p0, because what does that mean? That we just need our function evaluated at 1. And what is that? That's 1. So we have p0 is 1. P1 is going to be p0 plus, and what's our first derivative? Our first derivative is negative 2 over x cubed. So that evaluated at x equals 1 is going to give us what? We're going to get negative 2 over 1 cubed. So it's negative 2. So that means that we have our first term, which is 1 from before, and then we're going to subtract 2 times x minus 1, because we're centering at 1, to the first power. And then our second polynomial, or our second degree polynomial, is going to be what we had from before. But then we're going to have another term, and that's going to be found from our second derivative, which is positive 6 over x to the fourth. Do you see where the factorial is coming into play? And so then we have this evaluated at 1, so we have 6 here. And so we have a plus 6 times x minus 1 squared, and we got to divide by, which derivative are we taking? Our second derivative, so 2 factorial, which is 2, so I'm just going to be really lazy and write that as a 3. Okay? And then, last, we have our third degree polynomial, which is, and I'm going to be also lazy again, sorry, I'm going to write p2 plus, and then the next term that we're going to figure out, so our third derivative, which is going to be, can I just write this as 4 factorial? Negative 4 factorial over x to the fifth. And so evaluating that at 1, we have negative 4 factorial. And so we're going to have negative 4 factorial divided by 3 factorial, because we're looking at our third derivative, times x minus 1 to the third power. And so those cancel out, and we're left with negative 4 times x minus 1 cubed as our p sub 3. Okay, so that looks a little bit confusing, but we end up with like a line, like a horizontal line, and then another not horizontal line, and then we end up with a parabola, and then we end up with a cubic function. So let's look at what those look like. Let's see what those look like. So here I have, and I think I put a link to this in our post for this as well. So we have, let's see. So we have 1 over x squared. So our p naught, or our p0, is going to be just our horizontal line. And then here we have our p1, and look, now we have our slope matching up with our function. That's pretty cool, right? Our slope matches the red one, and I'm going to take off the blue. Okay, so that's a pretty good approximation, but as you get farther and farther away, like as you look at these values over here on our line, they're a lot farther away from what our red function is. So let's see if we can't get any better. Well, look at that. Wow. Just one more term in our polynomial, and look how much closer we get to our actual function value, at least on this part. Over here, it's ridiculous, right? That doesn't work very well at all. But over on this side, that's very good. It's a very good approximation. So I'm going to take off the green one, because now we have the purple and it's better. And let's see, can I click on this? So with our cubic, wow, wild, look at that. So now we have a pretty good approximation of what our function, our red one is, even on this side. And we got it to match up once. It's pretty cool. Okay, so just going for a third degree polynomial approximation for a not polynomial function, we can get a very good approximation for what that overall function f of x is going to be, just with a third degree polynomial. Just looking at it right there. It's pretty cool. It's pretty cool. I think I messed up though when I was entering that, sorry. So I think these need to be 3s. Which gets it even better, right? Yeah, it's a lot better. Okay, cool. But look, so good. Amazing. Math is so cool. Alright, so your task is to, for each of our functions, find formulas for the Maclaurin polynomial. So remember, Maclaurin is centered at 0. And and up to our third degree Maclaurin polynomials for our following functions right here. And also try to find a formula for the nth Maclaurin polynomial and write it using sigma notation. Also, use a graphing utility to compare the graphs, and probably use Desmos, use that, what we used over here as a jumping off point for that. And you're going to actually turn this in with your next problem set, so do get working on that. My recommendation, though, is to set up yourself with like a chart. So probably have like your f of x or f of a values, your f prime, your nth derivatives, and then your nth derivatives evaluated at a. So in this case, a is 0. And from here, you can pull off the numbers that you need for each of your polynomials. So carefully go through and construct these. And you should see a pattern, because if you think about like what are sine and cosine doing at 0, and what are their derivatives doing at 0, because sine of 0 is 0. The derivative of sine is cosine. Cosine of 0 is 1. So you're going to get some of this alternating canceling out of some of your terms. And see if you can think about, like, okay, so does that pattern make sense with what I understand of sine and cosine? Because sine, we know, is odd. It's an odd function, because it has, whenever you plug in the opposite, you get out the opposite. And cosine is even, because when you plug in the opposite of a number, you still get out the same thing. And so, cosine, does it make sense for cosine to be represented as an even polynomial? Like a polynomial with only even terms, even powers. And then with sine, does it make sense that it is a polynomial with only odd degrees? And then with e to the x, is there any sort of pattern that we can detect? Because with e to the x, we love e to the x. E to the x is great. It comes up in so many different ways, but try to think about how we can get a pattern for those. Okay. So, as I alluded to, you should definitely write these down. But write out the work and stuff like that. We have e to the x. It's going to be our sum from 0 to infinity of x to the n over n factorial. So, just writing out some terms here. That means that we have 0, x to the 0, which is 1, over 0 factorial, which is 1, so 1, plus x over 1, plus x squared over 2, plus x cubed over 6, or 3 factorial, plus x to the 4th over 4 factorial, and so on. With cosine, you can see that we have evenness is coming out, but we also have this alternating business. And the alternating is because, cosine's derivative is negative sine, so then that is going to toggle our sine back and forth between positive and negative. And the same thing with sine, that's going to have only odd degrees, and we're going to have a toggling between, or an alternating between positive and negative. Yeah, so please write these down. Alright, let's talk about remainder. So the remainder is where, very similar to with our alternating series test, we could give a like a interval that we knew our sum would add up to. With the remainder, we can bound what our polynomial is going to be like accurate within with the next term. So our alternating series, like if we were looking at the first 7 terms and we add those up, then we know that the difference between that sum and our actual value of our infinite series is going to be within that next 8th term, plus or minus of that, from the number we had before. With our Taylors, with our function and then our polynomial representation of that, where we're looking at a finite polynomial, the remainder between our function and our nth degree Taylor polynomial is going to be called the nth remainder. And that nth remainder is going to be bound by our next Taylor polynomial term. So we're looking at the nth remainder, and we're looking at the n plus 1th term of our Taylor polynomial. So that means that we take one more derivative, we divide by n plus 1 factorial, and we multiply by x minus 1 to the n plus 1 power. So we're everywhere we had, like where we stopped, we go one more term, and that is going to be our bound for what our remainder can be. So in math, we like to have things that are bounded by m's. I don't know why, but capital M is one of the favorites. So we're going to have a bound on what the value of this remainder is going to be. And it's going to be from, for all of our x values on our interval of convergence. An interval where this is going to work. Or a particular interval. It's not necessarily our interval of convergence, but on our interval that is containing our number that we're centering at. So what do you need to do for remainders? You need the next thing, and then you bound with that. So we need our first and our second Taylor polynomials for root x at x equals 4. So we're going to make our chart. F of x. And when is this happening? At 4. So we have, sorry, it's really bad. F of 4 is going to give us 2. So that's our 0th degree polynomial. Our first derivative, so f prime of x is going to be 1/2 x to the negative 3/2. Negative 1/2. My goodness. And so then evaluated at x equals 4, what do we get? 1 over 4. So our P1 is going to be 2 plus 1/4 x minus 4. And then our second derivative is negative 1/4 x to the negative 3/2. And so evaluating this, we end up with negative 1 over 4 times 1 over, what is x to the 4 is 8. 8. Yes, 8. Okay. So then we end up with what? Negative 1 over 32. And so we have our P2 is 2 plus 1/4 x minus 4 minus 1 over 32, but then divided by 2 factorial, so that's times 2 x minus 4 squared. Okay, so now we have our second Taylor polynomial, which is 2 plus 1/4 x minus 4 minus 1 over 64 x minus 4 squared. And then we need to estimate, so that's P2 of x. Estimate root 6. So that means that we're plugging in 6 for x into P1 and P2. So I'll pause the video, let you do that, and then I'll come up with your number. I'll meet you back here in a minute. Alright, so I put these into the TI and I hit graph, and so those are our graphs. The blue is the first one, that's our first Taylor polynomial, and the red is the second. I was kind of lazy with the 1/4 and I just did 0.25. I think it's the same number of keystrokes, so it doesn't really matter. But then we're looking at when we're evaluating at 6. So right here we got 2.5. It is our first Taylor polynomial approximation, and then 2.4375 is our second Taylor polynomial approximation. So that's pretty cool. And then we need to use Taylor's theorem to evaluate or to bound our error. So what do we do for that? Well, we need to take our next derivative, evaluate there, and see what we get. So let's do it. So our next derivative, or our f triple prime, is going to be from here, this -1/4 times -3/2. So that's positive 3/8 times x to the -5/2. And then we're going to evaluate that at 4, or at, we're bounding our error at 6, right, our root 6. So then, what's happening here? I should probably plug in the calculator. So we have that, and then put that in for my y3 for no particular reason. I guess we don't need that to be a line, but I wanted to look at it in the table. And then for checking's sake, I put in root x. And so let's look at our graph and look our, wow, it's really small. But our purple and our pink function and our red function are pretty dang close. And let's look at the table. So we have at 6, we have 2.4375 for our approximation with our Taylor polynomial of degree 2. And our actual value, according to our calculator, is 2.4495. And this term is evaluated at 4 is 0.0117. 0.0117. And so this is going to be our error bound, which it looks like it does work out, that we're within 0.0117. So that's it's pretty nice. We have a pretty close accuracy for just a couple of terms. Lovely. And we also know that we have Taylor series with all the derivatives that we need on our interval that contains where we're centered at A. Then this Taylor series is going to converge for all of our interval that we're looking at, if and only if. Remember, that's the IFF. If, especially if. Now, it means that we have both directions, that we have this limit of our remainder going to 0 implies that we have convergence for that Taylor series. And if we have convergence for this Taylor series, that implies that our limit of a remainder is going to be 0. They imply each other. For all of your x in that interval, that's containing A. And for some reason, we also in math like the interval I. That's another thing that you will see. So we need to find the Maclaurin series for cosine, then use the ratio test to show that the interval of convergence is all of our numbers. And then we need to show that our Maclaurin series converges to cosine for all real numbers. So I think we're probably going to use our remainder. And we're also gonna, oh, well, actually, you've done this already, right? You've looked at the cosine Maclaurin series. Yes, yeah. So, we have Maclaurin, which means that we're starting at 0. sorry, this is gonna be a long video. X equals 0. So we have f of 0, and that's going to be 1. And then we have f prime of 0. That's so this is cosine. So this is negative sine, and so that's but that's going to be 0. F double prime is going to be negative cosine, so that's negative 1. And then we have our derivative of that. Third derivative, our third term is going to be 0 because that's a sine, and we're going to keep on going through that cycle. And then, so this is our n equals 0 degree, first derivative, second derivative, third derivative. Okay. And then, so when we're constructing our Maclaurin series, then we have cosine of x equals 1 plus 0 over 1 factorial times x to the 1 plus negative 1 over 2 factorial times x to the 2 plus 0 over 3 factorial times x to the 3 plus 1 over 4 factorial times x to the 4th plus 0 over 5 factorial times x to the 5th minus 1 over 6 factorial times x to the 6th, and so on. So then all of our odd terms are going away, and we're ending up with, oh sorry, I should have this keep on going. So our Maclaurin series is our sum from n equals 0 to infinity of negative 1 to the n times x to the n over n factorial. But we need to make sure that we're only looking at even terms, so we need a 2 in there, because we're skipping all the odds. Okay, so we have our Maclaurin series. We need to show that our interval of convergence is infinite. Okay, so let's look at the ratio test, the limit as n approaches infinity. Love the ratio test, it's so great. Ratio test. The absolute value, negative 1 to the n times x to the 2 n plus 1 over 2 times n plus 1 factorial times the reciprocal 2n factorial over negative 1 to the, oh, this is n plus 1. n times x to the 2n. There's no reason to have parentheses there, but that's okay. Alright, so now what do we have? Well, we're thinking in our minds that 2n plus 2 factorial is going to be 2n plus 2 times 2n plus 1 times 2n factorial, right? That's what we're thinking. So then that and that can cancel out. This is a 2n plus 2, so that means that this x to the 2n and this x to the 2n can cancel out, so we're just left with an x squared in the numerator. I should probably write these down. And this is all like algebra, right? This is like very annoying algebra, but it's algebra nonetheless. And then our signs will just go away because of our absolute value. And then we have x squared in the numerator, and we have 2n plus 2 times 2n plus 1 in the denominator. And that's lovely because our numerator has no n's, our denominator has n squared. So this is going to give us 0, which is less than 1 for all x's in our numbers, in our real numbers. So that's nice. And we end up with our interval of convergence is from negative infinity to infinity. And, well, let's think about how can we show that this converges for all real numbers in x. Well, I wonder if we can use this, our remainder. Because Taylor works for, the Taylor remainder works for Maclaurin also, right? Because it's just a special case. So let's think about this. What is our next term in our, I'm going to write this down here. What's our next term in our cosine? Well, that's going to be -1 to the n times x to the 2n over 2n factorial. Our next term after this is going to be -1 to the n plus 1 times x to the 2n plus 1 over 2n plus 1 factorial. Sorry, 2n plus 1. So we have this as our next term. Now what's going to happen as n approaches infinity of this? Well, this doesn't matter, right? This is just changing our sign. And then as n approaches infinity, what are we ending up with? We're ending up with an n factorial in the denominator, and then we're raising some x value to a 2 to the n plus 1. So do we get out a 0 there? I think so. And so, because factorial is going to grow faster than any exponential thing that's going to be happening. And so we end up with convergence for cosine for all of our x's, because this goes to 0. And that's the remainder that's going to go to 0. Wow, so much. But this is a good strategy. Writing out terms is important. Also, keeping track of what you're looking at, like having a column for your index. Write these down, please. Use Desmos. This Desmos is good. Now I fix a typo. And Taylor series and Maclaurin series are the same thing, except for Maclaurin is centered at 0, whereas Taylor are centered at any number. It doesn't have to be 0. And that is it. These are the most useful, but also possibly the most confusing. And it is okay to be confused. Don't fret. Just keep on trying. And ask questions if you have any questions. Alright, bye.